Hi, good morning. Good morning to everyone. And this is C. Kumar sir. Today, we are going to discuss static fluid. And welcome to everyone, the GateMentorAcademy.com. See that static fluid means the fluid will be at rest. And if the fluid is at rest, it means there is no motion of the fluid. Means the shear stress will be zero. And if the shear stress is zero, the viscosity also will be zero. And if the viscosity is zero, that type of fluid is called here ideal fluid. That type of fluid is called here ideal fluid. And in static fluid, we will discuss a three subtopic. It's pressure measurement, hydrostatic forces, and buoyancy. First of all, we'll start that pressure. The pressure is always due to point of application of force. Point of application of force. If the force is acting one point, at that point, the pressure will generate. At that point, the pressure will generate. And the pressure unit is a Newton per meter square. So the stress and the pressure both has the same unit. It's a Newton per meter square. But the pressure is due to the point of application. But this stress is due to the whole cross-section area. That the force should act on whole cross-section area. And due to that, the stress will generate stress. And that force, it could be tensile force and compressive force in stress. But in pressure, the force will be always a compressive force. It will be always a compressive force. So the third point, we can define the pressure. It's a force per unit area is called a pressure. Force per unit area. And it's a Newton per meter square. So the force is always here compressive force. So we can prove that whether the pressure is due to point of application of force or due to the cross-section area. So that one we can indicate in Mohr's circle. We can indicate in Mohr's circle. And if you assume that there is a two-dimensional, so this side is a sigma and this side is a sigma, and these two are here pressure only. Because the force will be always compressive in nature. So we have a maximum shear stress formula, and that indicates that radius of Mohr circle, and that is given as sigma x minus sigma y divided by 2. So this represent here sigma x and this is the sigma y. Both are compressive. It means minus sigma and this is also minus sigma. If you substitute here, you will get it here 0. The shear stress is 0. Maximum shear stress is 0. Then the radius of the Mohr circle is 0. It means the circle will convert it to a point. Circle will convert it to point. And to draw the circle, this side will represent the normal stress and this side it will represent the tau xy. That is a shear stress along a xy plane. So shear stress is 0. It means the Mohr circle will convert it to a point. So here I prove that the pressure is always due to the point of application of force. Next, we will see that here different type of pressure. So there is a, I will indicate it here. There is a XY plane is there. This x-axis is indicated as zero pressure. Zero pressure. Zero pressure means the pressure which is measured at 0 Kelvin. It is called here zero pressure. And this side is here pressure axis is there. This side. So I'm going to take the one reference pressure, and that reference pressure is called atmospheric pressure. Atmospheric pressure. And atmospheric pressure is given as 760 mm of Hg. And that one you can write on 101.32 kilopascal. So the pressure which is more than atmospheric pressure is called a gauge pressure. So this is called here P gauge. P gauge pressure. And the pressure which is below the atmospheric line, it is called here P vacuum pressure. P vacuum pressure. So there is two types of pressure are there. Gauge pressure and another one, it's a vacuum pressure, and another one is called here absolute pressure. And this gap is also called here P absolute. So we can write on here P absolute pressure is P atmospheric pressure plus P gauge pressure. P atmospheric plus P gauge, that is from here to here. And this is here absolute pressure. And one more, the P absolute will be P atmospheric minus P vacuum. So here the vacuum pressure, it will be negative. Negative. And the gauge pressure is above the atmospheric pressure, it means it's a positive. So here I can say that the gauge pressure could be a negative or positive, but the absolute pressure is always positive. The gauge pressure could be positive or negative, but absolute pressure will be always positive. So here the gauge pressure and absolute pressure, we have defined that here. And zero pressure also we have defined that. So you can look at it here. And vacuum pressure means what? The pressure below the atmospheric pressure. And below means it will represent some negative. Or gauge pressure means the pressure above the atmospheric pressure. Pressure above the atmospheric pressure is called here gauge. Absolute pressure, which is measured with respect to zero pressure level. Because whatever the absolute pressure we have indicated here or here, that is with respect to this x-axis. So we can say that here the P absolute measured with respect to zero pressure line. Zero pressure line. Next, we will see that here Pascal's law. Pascal's law, what it says that the pressure applied at any point is equal in all the directions or diminished equally in all the directions. The pressure, force applied, okay, the force applied at any point diminished equal in all directions. So if you say that any one point, like I'm assuming that one right angle triangle. So if I say here, the pressure in this direction, upward direction, and in Z direction, the pressure must be equal. The pressure must be equal at any point in all the directions. Remember that. That is called here Pascal's law. So there is an application of Pascal's law is there. Application of Pascal's law in jack, hydraulic jack. So I am going to assume that there is a jack is here, and this is called here ram, and the ram area is A. This is a ram, and I am going to apply the force F1 at this point. And another thing, this is called here plunger, and plunger area is a small a. And the output force, I am assuming that here F2. So this is here output, and this is here input. So here we can, and this jack is filled with a lubricant that is in liquid state. So if I'll say that here, whatever the pressure generated, whether at this point or whether at this point, yani along a horizontal plane, if I'm assuming that this is the B and this C, so by Pascal's law, we can say that along a horizontal plane at any point, the pressure must be same. And the F1 by A must be equal to F2 by small a. So the here F1 is equal to, we can say that F2 into A divided by small a. So since we know that capital A is greater than a small a, so the F1 must be equal to F2. F1 must be equal to F2. So this F1, I am assuming that it's a output force. And this F2, I am assuming that here input force. So the here arrow is, you can reverse it here, arrow it's a downward, this one, and this is the upward. And this is output. And this is an input here. This is output and this is input. So using this Pascal's law, we can solve it here any type of questions based on that. Next, we have one more law. That law is called here hydrostatic law. So let us assume that one elements are there, fluid element. And the fluid element depth, I am assuming that dH. And the fluid pressure, and this is here under the submerged body. And the fluid pressure at the inlet, I am assuming that P into dA. And the cross-section area of this part is here, dA is there. And the outlet pressure force, I am assuming that P plus dP into dA. It's a little bit more because the output force must be more than input force. And this is here element is there, fluid element. So there must be a weight of this fluid element. And the weight of the fluid element will act downward. So if I'll say under equilibrium, the downward force must be equal to here upward force. Downward force must be equal to here upward force. And the downward force is PdA plus weight of the element. It's a rho Vg. This is the weight of the element. And the upward force is P plus dP into dA. So this PdA, it will get cancelled. Density. Volume we can write on here, area into height. It's a dA into dH. The height of the fluid element is dH into G is equal to dP into dA. This dA get cancelled. If you write on here dP by dH, it will be equal to rho into G. And this rho into G is called here a specific weight. So if you separate the derivative rho G into dH, and if you integrate it here, So the P will be equal to rho GH plus C. There's a constant C. So if I am assuming that, let's say that this is the free surface of water is here and the whole body is submerged. So if I'm assuming that if height is equal to 0, so if the height of any body is 0, it means that body will have a atmospheric pressure. Remember always, when the height becomes 0, the pressure will be atmospheric pressure. Any body which is always contact with atmospheric pressure. So it will be here P ATM and the height is 0 plus C. So C is equal to here P ATM. So the P will be equal to rho GH plus P ATM. But if you say for a gauge pressure, because the gauge pressure is always measured with respect to atmospheric pressure, so I'll assume that P ATM is 0 for gauge pressure. For gauge pressure, the P ATM must be equal to 0. It means the P gauge will be equal to rho GH. It's very, very important to solve the problem based on atmospheric pressure, because a atmospheric pressure is defined as here 760 mm of Hg. So if you apply that same thing and if you find out the here gauge pressure, so 7 density Hg means mercury is there, and the mercury density is given as 13,600 kg per meter cube. So this is the 13,600, 9.81, and 760 means 0.76. And if you multiply them, you'll get it definitely here 101.321 kilopascal. Next, we have an application of pressure, like how to measure the pressure. And the topic is here pressure measurement. So the first important manometer is a piezometer. Piezometer is used to measure the low pressure intensity. And the second thing is it's a simple in design. Like there will be a one gauge, and this is called your gauge, and we have to measure the pressure at this point, and this gauge is connected to through the pipe here. It's a pipe, and this is the point A. I need to measure the pressure at point A, and this gauge is filled with a liquid, and there is a mercury is there. Why the mercury is used to measure the pressure? Because the mercury has a non-sticky liquid and the high density. Non-sticky means there will be only force of cohesion. So height, I'm assuming that from here to here, it's a H is there. Okay, just a minute. This is not a. This is a U2 manometer. Piezometer, it is a like that. This is the piezometer, and there is a rise of liquid in the piezometer is through the height H. And let us consider the height is H, and the density of that liquid is rho. And we need to measure the pressure at point A. So what to do? Draw a one line. Draw a one line, and you assume that this point is B. So I can say that by Pascal's law, the pressure at B must be equal to pressure at A. So pressure at A is equal to pressure at B is given as rho GH, because the height, we know that this is your reference line. Always try to take the depth from the reference line, and the density is given rho, and we have a 9.81, that is acceleration due to gravity. So the formula to find out the pressure at point A, it's a rho gh, and that indicates that here gauge pressure. Gauge pressure. So like any type of liquid, if there's a water is there in that, so water means you just put it here. Water density is a 1009.81, and the height, if it is given here 1 meter, so write down the 1, and the answer will be here 9810 Newton per meter square. So this is the first type of meter is there here, that is called piezometer. And the next we have a manometer. Which manometer? It's a U-tube manometer. The U-tube manometer is used to measure the high pressure intensity. High pressure intensity. So with the help of manometer, we can measure two types of pressure, like the positive gauge pressure, or else we can measure here negative gauge pressure also, negative gauge pressure. And that negative gauge pressure is called here vacuum pressure. Vacuum pressure here. So we'll construct here, first of all, first step is here gauge pressure. Like this is the gauge is here, and this is the U-tube gauge, U-tube manometer is there, and we have to measure the pressure at this point. And after that, there's a mercury is there, and that is up to this height. And this mercury height is given here, it's a S2, and this height it is given here, it's a H1. And density of this one is rho1, and density of the mercury is a rho. So I will consider the one reference line. Where should I select the reference line? So the line where the fluid changes. Fluid changing. So this is a one fluid that having a density of rho1, and this is the mercury. So at this point, the fluids are changing, and I'll always select the lowest level. So you create a one line, and that line is your reference line, and consider the point B at this point and C. So by Pascal's law, we can say that the pressure at B must be equal to pressure at C. And the pressure at B will be equal to left limb pressure must be equal to a right limb pressure. So these are the called here limb. This is also a limb, and this is also a limb. But this is a right limb, and this is here left limb. The left limb is here PA plus rho1 G H1. Because the density is rho1 and the height is H1, is equal to right limb. The right limb is rho2 G S2. So the PA will be equal to rho2 G S2 minus rho1 G H1. So this is here a gauge pressure. That is a pressure at point A. And it will be always a positive because the height is more than H1. So it will be always a positive. Next, I will see that here, third is a vacuum pressure. So vacuum pressure itself, it's a negative pressure because it's a below atmospheric line. So you make it here one gauge, a U-tube manometer. And we need to measure the pressure at this point. And there is a liquid is there up to this side, and there is a mercury is there up to this side. So I will select the label where the fluids are changing because these are the gases here, and this is the here mercury here, and the mercury density is rho2, and this liquid having a density is rho1. So I will select this is my reference line because the liquid is changing at this place also, at this place also. I'll select the lower line, and that will be my reference line. You consider this point is B and this point is C. By Pascal's law, we can say that the PV is equal to PC. And this is the left limb pressure must be equal to a right limb pressure. The left limb is PA plus ρ1G H1 plus ρ2G H2. And this side is your atmospheric pressure is acting, but I am finding your gauge pressure. It has atmospheric pressure as well here, a reference pressure. So the PA will be equal to minus of ρ1G H1 plus ρ2G H2. Negative. So that negative indicates that here vacuum pressure. I'll continue that after that. Okay, so we will check the problem based on the pressure measurement. So we have a very first question. The pressure have been observed at 4 different points is a different unit as follows. Arrange them in descending order of the magnitude of the pressure. So the option number A is given in kilopascals. Directly it is given in kilopascals. Just a minute. Okay. So it is given here 150 kilopascal. It means 150 into 10 raised to 3 Newton per meter square. Because the pressure is indicated by here Newton per meter square, or it's a Pascal, or it is given as a bar also as a unit. Next, it is here 1800 millibar. So write down 1800 milli. So milli you convert into meter. It's a 10 raised to minus 3 meter, and 1 bar is equal to 10 raised to 5 Newton per meter square. 10 raised to 5 meter per second square. So if you simplify them, so you'll get it here 180 kilopascal. Because here 10 raised to minus 3 and 10 raised to 5, and you'll get it here 10 raised to 2. Take out 1 0 here, 10 raised to 3. The remaining is 180 kilopascal. Similarly, the next is 20 meter of S2. The head is given. This is a head actually. 20 meter of S2, it means it's a head. And P is equal to it's a rho GH. And P by rho G. This indicates that head. This is called a specific head. And that indicates that height also. So it's a 20 meter of S2. The pressure is indicated by like that also. And to convert this one into pressure, you apply the formula rho GH. S2 is given, it means water. The water density is 1000, 9.81, and the 20 is there. If you multiply them, you will get it definitely 196.2 kilopascal. And the next one, 1240 mm of Hg. They apply the same formula to find out the pressure. So Hg means 13,600 is the density. G is a 9.81 and the height is 1.24. And if you multiply them, you'll get it here 165.45 kilopascal. So we have to arrange them in descending order. It means the first one, it will be C first. Then, first of all, C. Then it is a B. Then it is a D. Then it is a A. And a list of them is here. Option number A is correct. Next, we'll move to the question number 2. And it is given that the pressure gauge G1 and G2 installed in a system shows on a pressure PG1. It is given that here 5 bar. The pressure at this point, it is given 5 bar. And the PG2 is a pressure, it's a 1 bar. Here it is given 1 bar. At the atmospheric pressure is 1.01 bar. Then find the unknown pressure P in an absolute scale. So whenever they are asking the absolute, to find out the absolute, you need to use P gauge plus P atmospheric. And you need to add atmospheric. So first of all, find out the PG2. First of all, to find out the PG2, add Pg2 is 1 bar and atmospheric pressure is 1.01 bar, yani 2.10 bar. So the pressure at this point, I got it here, 2.01 bar. Now to find out the Pg1, like I need to find out the pressure at this point. Pressure at this point, it will be here Pg1 plus pressure at this point. It's a Pg2. So Pg1, it's given here 5 bar plus 2.01 bar, and it will be equal to 7.01 bar. So this indicates that pressure at this point. And first of all, find out the pressure at this point, and we have added atmospheric pressure. After getting this pressure, to find out this pressure, add this pressure plus this pressure. You'll get it here, the pressure at this point. Because the pressure varies according to the heights. So it's a 7.01 bar. It's option number A is right answer. The next option we'll see that here. An open tank contains a water to a depth of 1 meter. Open tank is there. And the water is 1 meter and the oil is to depth of 1 meter. And the density of oil is 800 and the pressure intensity at the interface of the two liquids. So first of all, there should be a water because the water is a more dense and the height of the water is given 1 meter. This is the water is there and the water density is 1000. And after that, there is a oil is there. Because the oil density is less, it means the oil will be in floating condition and the oil is 1 meter. And the density of oil is given here 800 kg per meter cube. So I need to find out the pressure intensity at the interface. So this is my here interface. So I'll go from the up, whether you go from up or down, but the pressure varies according to the height. So pressure intensity at the interface means this is my interface. So I'll go from the up, it means the height is 1 here. So I'll apply the P interface is equal to rho GH. So rho means it's the oil is there. This is your oil, only oil, into 9.81 into height is 1 meter. And if you simplify them, you'll get it here approximately 7 kilonewtons per meter square. The option number B is there. If they'll ask you to find the pressure at bottom, it means you need to add the pressure due to the oil and the pressure due to the water also. Pressure due to the water also. That is the pressure at the bottom. But if they'll ask you the pressure at the top surface, it means the pressure at the top surface is 0. And that is the atmospheric pressure. That is atmospheric pressure because at height is equal to 0, the pressure will be here atmospheric pressure. But whenever you are measuring the gauge pressure, the atmospheric pressure taken as a 0. Next question we'll see that here. Select the correct combination of a statement from the following for a fluid at a rest. If the fluid is at rest, in equilibrium, the pressure must be same over a horizontal plane. That is correct. If I'm assuming that this is the plane is there, so over at any point in a horizontal plane, the pressure must be same because the pressure varies along a downward direction or in vertical direction. So this is correct. Density must be same over a horizontal plane. Yeah, that is correct also. That is also correct because it's an isotropic material. So everywhere the liquid density is the same. And next, shear stress must have a non-zero value over a horizontal plane. And that is correct. Shear stress will have a 0 on horizontal plane, non-zero. And dP by dH is equal to omega. No, the C option is wrong because the shear stress, it should be 0 because the fluid is at rest. It means it should be 0. The D option is right. dP by dH is omega. So the option number here ABD. ABD means the option number C is right answer. Next, we'll check it here. The standard atmospheric pressure is 762 mm of Hg at a specific location. And the local atmospheric pressure is 700 mm Hg. So local atmospheric pressure is given. It's a 700 mm of Hg. And this is given here a gauge pressure 762. It's a gauge pressure 762 means it's a 762. What will be, what does an absolute pressure of 380 mm of Hg corresponding to? And that is given in vacuum. Okay. So the absolute pressure must be here negative. It means this pressure is given here 380 because it should be 700 is this one, and 380 mm of Hg it should be down. So this indicates that here vacuum pressure. This indicates that vacuum pressure. So this gap is given as P absolute pressure also. And P absolute is given as P atmospheric minus P vacuum. P atmospheric is 700 minus 380. And if you take the difference, you'll get it here 320 mm of Hg. It means the answer is option number A is right answer. Next, we have a next question. The specific weight of the ocean water changes according to the equation W is equal to W naught plus C into root under H, where the W naught is a specific weight of water at the free surface of the liquid. Then find the pressure as a function. So to find out the pressure, we have a hydrostatic law that dP by dH is equal to omega, and the omega is given omega into C into root under H. So dP is equal to omega naught plus C into S to power 1 by 2 into dH, and integrate it here. So P is equal to omega naught into H plus C into S to power 3 by 2 divided by 3 by 2. See, if you simplify them here, you will get it at 2 by 3 C S to power 3 by 2. So the answer will be here, option number C is matching here. So you need to just integrate it here and you need to do that. Next, it is given there are 3 immiscible liquids having a density rho, 2 rho, and 3 rho. And their corresponding height is also given here, 3h, 1.5h, and h. Kept in a jar, the height of a liquid in a jar and the piezometer fitted to the bottom of the jar is given. Find the height ratio. So what you do, or write on the left limb pressure must be equal to the right limb pressure. So I'll take the reference line. I'll take the reference line, this one. This is my reference line. Or else you can write on the pressure at this point, or else you can take the reference line, this one also. It won't create the problem. I'll take it here, no problem, because this is a same liquid here. Right on the, let's say that this is the A point and this is the B point. The pressure at A must be equal to pressure at B. So pressure at A is rho GH. The first called 3H is height and density is rho. Rho into 3H into G. And next, 2 rho is a density and the height is 1.5H into G. It must be equal to, what about this height? So ये जो height होगा, it will be H minus small h. And that will have a 3 rho into G into capital H minus small h, because the height for this liquid is H minus small h. Because this is my reference line. So if you simplify them here, simplify them, so rho and G will get cancelled because both the side. So it will become 3 to the 6H plus 1.5. No, here it is only 3H is there. 3H here. And 1.5 into 2, again 3H must be equal to 3H minus 3H. So if you send it this side, this will be 9H is equal to 3H. So the H by a small h ratio is a 9 by 3. It's a 3 by 1 is a ratio. So 3 by 1 means it's a C option is the right answer. You can take this reference line also. It won't create any problem. C and D. So you need to write on the rho into 3H into G plus 1.5H into 2 rho into G plus H into 3 rho into G must be equal to H into rho into G. If you simplify them here, you will get it here 3 ratio. So the option number C is right answer. And I'll keep this much only for today's. In the next class, we will discuss the problem based on piezometer and U2 manometer and the differential U2 manometer and single column manometer. So in the next video, we will create the concept behind that and the numerical question based on that. And these all are the previous year question paper. So thank you everyone